Good afternoon here. This is Schweitzer looking at the next series of videos of School of Acid and Base. Can I interpret or model a strong acid? So pretty important. One, you should know the 6 strong acids: HCl, HBr, HI, HNO3, H2SO4, and HClO4. In this case, you should understand that they go 100% to completion. So any model would indicate that. You would never see these things together. You'd only see them separated or have gone through hydrolysis. The typical beaker or model that I might draw is I would compare this to, let's say, a weak acid. And I don't know that I want to model just one of them. I'm gonna model both of them. And in this situation, we're just going to draw out 4 beakers. So you can follow along here. Hopefully this works out. Alright. Moving slowly here. Alright, so we got 4 beakers here. And the bottom 2 I'm going to consider to be weak acids. Okay. And the top one is considered to be strong. So the top ones go to what we call completion. The bottoms we go to equilibrium. They all will follow the same exact formula reaction. HX plus H2O yields H3O plus X negative. The top one just goes 100% to completion, and the bottom one has both a forward and a reverse reaction. So it turns out that for all, it's kind of all or none type situation. The strong acids, let's draw those out. It's just going to be, now I'm going to go concentrated strong acid and dilute strong acid. So the concentration has nothing to do with the strength. That's how many you start with. Alright. So let's say strong involves 6 atoms. I mean, I should say strong concentrated. So I'm going to draw 6 HCl's, but they've already gone through hydrolysis. Let's say HX. I'm going to use 6 of them. 6 HX's. But you wouldn't see HX. You would see H. I'm going to go H plus, X negative. H plus, X negative. H plus, X negative. H plus, X negative. 1, 2, 3, 4. Sorry. And then I need H plus, X negative. 3, 4, 5. H plus, X negative. Okay? So I now have 6 of them. You can circle them here. And they're all gone through hydrolysis. Then you have what's called a dilute strong acid. Just means I don't have as many of them. I'm going to say dilute is going to be 3. H plus X negative. H plus X negative. H plus X negative. Okay? But notice the 3 I have all 100% gone through hydrolysis. Now let's go through a weak acid. Now, weak acid is one where there's a dominating reverse reaction. It turns out that for almost all reactions involving weak acids, the reverse reaction is much more prevalent, much more dominant than the forward reaction. These top strongs are all product favored. But weak acids are all reactant favored. which means that when you get to your stalemate, there's a lot more reactants there than there are products. And in fact, there's more than just a lot. It's like almost all. And in fact, if I were to draw a strong acid, a weak acid, someone might even draw it like this. They may draw all 6. This is a concentrated weak acid. Now, in this case, I'm not showing any products. And the reason for that, you can draw one. I could eliminate one of these guys and go H plus and X negative. Okay, so these guys went through the reaction. Great. This is showing that 1/6 of my particles went through hydrolysis. And this is through the stalemate situation here. That in this stalemate situation, I have 1/6 of my stuff at products, 5/6 of my stuff at reactants. It just turns out that for weak acids, that's too much. And in fact, usually it's 1 to 2 or 3%, which means that if I want to accurately show how many products I really have, I might need to draw 100 of them and then show 1 or 2 of them being flipped to products. So very often, if you want to draw like this, you can, but very often, the way I might draw it is just where this just stays HX. And we notice just that that's just more realistic. That's what it really looks like. And then a dilute weak acid is one where there just isn't as many of them. But again, they stay pretty much all as reactant. Is there a small amount of H or plus ions present in both these? Yes, but as we get more into the next videos, we start calculating out the actual concentrations, you'll find it to be quite small. Right? Thank you very much. This is modeling both strong and weak reaction acids.